Alright, now we are moving into the last topic of topic 2, right? Last subtopic, which is on Laplacian. So as I mentioned earlier, right, in my previous class, we have done line integral, the first subtopic. Then we spoke about surface integral, second subtopic. Then we have volume integral, the third subtopic. Then we talked about gradient, the beginning of del. Then we talked about divergence theorem, which is subtopic 5. Then we have curl, Stokes theorem, which is subtopic number 6, and this is the subtopic number 7, which is Laplacian. Right, so this Laplacian, right, the formulas, there is Laplacian of a scalar, and also there is formula for Laplacian of a vector. Just that in our syllabus we don't talk about Laplacian of a vector. So I make a note here that we just learned Laplacian of scalar, right? So even the formula of vector, we took it out. All right, so in your formula sheets you can only see one Laplacian formula. So what is the symbol of Laplacian? The symbol of Laplacian is this one, del squared V, right? So del V is gradient, right? So this symbol is gradient, right? So del multiply with scalar, you get gradient. Del dot vector, you get divergence, diff. Del cross A, you have curl. And this is Laplacian, right? Del squared V. So take note of the symbol, right? So you should be able to identify these symbols in your formula sheets. So this is 1, this is 2, right? So we differentiate the gradient with Laplacian in that manner. So Laplacian of a scalar, the answer is also scalar, right? So the answer is scalar, right? So easy to remember, vector, scalar, vector, scalar, right? So it alternates lah. So why is it so? Why might it be scalar, right? So let's take a look at definition. What is Laplacian? Laplacian is the divergence of gradient of scalar V. So this is the definition of Laplacian. This is scalar, this is scalar. But when you apply the gradient formula, right, it becomes a vector. Vector dot with a vector, the answer is scalar. So that is why Laplacian is actually, the end product is scalar, right? So divergence of gradient of scalar V is Laplacian, which is scalar, right? So what are the formulas? You should be able to identify these two formulas in your formula sheets, right? The first one is for Cartesian system, quite straightforward. And the second one is in terms of cylindrical coordinate system, right? Just be careful, right? The order here, you have to do this first. Then you have to times with rho. Then you have to differentiate by rho. Then you have to divide by rho, right? Do not cancel this row with this row. If it's cancelable, they would have cancelled for you, right? So it's not that they are asking you to cancel, no, because there is a bracket, so the order is here. So you have to differentiate first, then you times with rho, then you differentiate by rho, then you divide by rho again. So 4 steps. And do not forget this constant, right? So cylindrical, just be careful when you're applying the formula. So where do we apply this? We apply this to find the capacitance and resistance derivation, right? So that is a topic on its own, topic number 5, right? So under electrostatics, we have the first topic in free space, second topic is on medium. The third topic from now, all right, this is topic 2, so the third topic from now is topic 5. It will be the derivation of resistance and capacitance using Laplace equation, which comes from Laplacian. Right, so we will use that more in that particular topic. At the moment, we will use a bit less lah. We just touch and go to tell you that this is the formula and how to use the formula, and that's it for now. Okay, so later in the third topic from now, you will talk in detail, right, on how to use this in terms of doing some derivations. So let's do some derivation now without further delay. All right, example 3.11. Let's talk about part A. You are given Cartesian scalar, and you're supposed to find the Laplacian. So let's apply the formula, del squared U. How do you do this, right? So this is second order, means you have to differentiate 2 times. So what I like to do is I differentiate once first, right? So I break up my work in this manner. So I differentiate once, I put it inside the bracket. Then the next step, I differentiate again, right? So by doing that, I'm doing two different differentiation, right? If you are doing it one go, there is high chance you might make a mistake because you're trying to do it in your mind. So that is why I prefer for you to break it up, right? It's up to you how you want to solve it. If the answer is wrong, you get no marks. If the answer is correct, you get your full mark. Okay. So let's break it up. Now this is better. That means I'm trying to do the first order differentiation, then we do the second order differentiation in the next step. Alright, so just substitute as we go on. So I'm supposed to differentiate this in terms of x, the first product. So when I differentiate in terms of x, I get 2x, y is constant. X squared becomes 2x, y is constant. When I differentiate the second product, x becomes 1, yz is constant. So next part is in terms of y differentiation. I have to differentiate this in terms of y. First product, x squared is constant, y becomes 1. When I differentiate x, y, z, and then I will get x and z is constant, y becomes 1. So what are we trying to do is we are trying to differentiate y. So y becomes 1, y becomes 1. Next part, differentiate in terms of z. So what happens? First product is 0 because there is no z. Second product, z becomes 1. So this is just half of the answer. We are not done yet. You have to differentiate one more time because you are looking for Laplacian. So when we differentiate in terms of x, you get 2y. This is 0. In terms of y, 0. In terms of y, 0. This is already 0. And in terms of z, 0. So what is the answer? The answer is 2y, scalar. Right, so just apply the formula. Right, so this is the formula that we are supposed to solve for. So my proposal is you break it up into first order, first order, first order. Then the second order comes in your next step. By doing that, you are doing second order differential equations. So moving on, let's talk about the part B because we have to apply this formula. And it's a bit lengthy, so we have to occupy some space. Okay. So we are looking for del squared V. So let's break it up. 1 over rho. Oh, it's already broken up there. So we just need to bracket. We just need to find this. Okay. Because this is not enough space. Okay, let's do one immediately, right? So I have to differentiate this in terms of rho. So when I differentiate this in terms of rho, rho becomes 1. So z sine phi plus next product, there is no rho, 0, plus last product, 2 rho. So what I've done here, I've just solved for part 1 where I am supposed to differentiate v in terms of rho. Rho becomes 1, z sine phi. There is no rho, 0, and rho squared becomes 2 rho plus 1 over rho squared. This one we have to break it up into first order. So when you break it up, differentiate first one in terms of phi, rho z cos phi. The second one, it's a bit cos squared, right? So if you've forgotten how to do this, so let's just do a quick refresh. Cos squared phi, when you're trying to differentiate this in terms of phi, is actually differentiation of cos phi squared. So when you differentiate this, the 2 goes in front. When you differentiate cos, right, so power becomes 1. When you differentiate cos, the answer is negative sine. So using the double angle notation, this is equals to negative sine 2 phi. Right, again this step is optional no? Because it's just simplifying this entire expression. Instead of writing it in this manner, you can write it in this manner if you remember your double angle identities. So this here is negative sine 2 phi. And the last one is 0. Because why? There is no phi here. So I'm supposed to differentiate this in terms of z. So when I differentiate this in terms of z, first product, z becomes 1. So rho sine phi. Second product, z becomes 2z cos squared phi. 2z cos squared phi. Right? And the last one, there is no z. So answer is 0. So this is the first order differential equation. So we have to continue with the second order. So 1 over rho. So differentiate this. We have to times with rho first, remember? Right? So my second step is to times with rho. So rho times with this, it's rho z sine phi. Differentiate by rho, you will get z sine phi because rho becomes 1. Repeat again, rho z sine phi then you differentiate by rho, rho becomes 1, so z sine phi, plus rho times with 2 rho is 2 rho squared, then you differentiate by rho, you get 4 rho. Okay, so multiply first, you get 2 rho squared, right? And then when you differentiate 2 rho squared, the answer is 4 rho. 1 over rho squared, differentiate phi, rho z is constant, cos becomes negative sine, and this is minus sine 2 phi. When you differentiate negative sine 2 phi, you get cos 2 phi, right? And then the differentiation of the angle is this 2 goes there. For z component, differentiate the first component in terms of z, don't have 0. Differentiate the second component in terms of z, 2 cos squared phi, because z becomes 1. And let's put them together. Let's see whether does it cancel out or not, or is it going to be one long expression. So this is the answer for del squared v, which is z sine phi over rho plus rho and rho will cancel, for 1 over rho squared rho z, so rho and rho will cancel, we have negative z sine phi over rho, this is 2 cos 2 phi over rho squared plus 2 cos squared phi. So we can reduce this and leave the rest as it is. Right, so I'm done with this example. Right, so example 3.11, what are we trying to do is just apply the formula, and then once you have applied, you see, right, you perform the differentiation, especially for cylindrical system. Be extra careful. There are 4 steps here. 1, then first step, differentiation of rho, first order, then you times with rho, then differentiation of second order, then you divide by rho. Okay, so this one is quite straightforward. You have to differentiate 2 times, right, and then divide by rho squared. Last one is easy lah. Z is always the same. So we've done with this example. Let's move on with this test 1, special SEM 17, 18, and you're given scalar u. You're supposed to find A, which is the gradient, B, which is the curl of gradient, C, which is the Laplacian, and D, you're supposed to determine the divergence of gradient u, and you're supposed to evaluate this expression at point P, and you're supposed to tell whether is it a source or is it a sink, because this is divergence. The bigger process here is divergence. So we talked about divergence, and there are 3 conditions: source, sink, and not source, not sink. So we are supposed to evaluate at a particular point, in this case point P, and if we get the answer is negative, that means it must be a sink. If we get it's positive, that means it must be a source. If it is 0, means it is not source, not sink. So this is the application because we have studied all 4 now, right? Gradient, divergence, curl, and Laplacian. So we are trying to apply the formulas for one question. Okay, so that would be our next class, sorry, next example, which is now. Alright, so let's talk about part A. I'm looking for gradient. So remember the gradient formula, right? This gradient formula, it is in terms of vector, because it is a vector. For Cartesian, is quite straightforward. So I have to take u, which is the entire thing. Both products are u. Differentiate this in terms of x to get my x component. So when I do this, I'll get my x component. So differentiate xy in terms of x, we get y, because x becomes 1. Differentiate y squared z in terms of x, there is no z. Sorry, there is no x, therefore answer is 0. Next, differentiate xy in terms of y. Alright, so x and y becomes 1. Differentiate y squared z, y squared becomes 2y. And when you differentiate xy in terms of z, 0. When you differentiate y squared z, z becomes 1. So this is the gradient, right? So we have done this before. In case you forgot, better refer to your formula sheets, get your formulas and try to do your substitutions yourself. Straightforward. Part B, you're supposed to find the curl of del u. See, you can't do this. This is wrong. Why is this wrong? Because this is scalar. Curl is cross product. Cross product you must do with a vector. So hence you can see we have del u. Del u is a vector. Gradient is a vector. U is a scalar. Del u is a vector. So del cross del u. We can do this. But we cannot do this. Right? So mathematically this is wrong. But we can do this because it's a vector. Okay? So just be aware of the notations that you see there. Right? So sometimes it just looks like u, but it's actually not u anymore. Right? It becomes something else, which is gradient, which is a vector. So we have to apply this formula, right? Z component, we need to differentiate this in terms of y. So it is 2y. Y component, I need to differentiate this in terms of z. There is no z for the first one. For the second product, there is z. Z becomes 1 and 2y. Then x component, I need to differentiate this in terms of z. There is no z, 0. Z component, I need to differentiate this in terms of x, 0. Move on. Y component, I need to differentiate this in terms of x. X becomes 1. And then there is no x here, 0. X component, differentiate this in terms of y. Y becomes 1. So let's simplify it. This is 2y minus 2y, 0, 1 minus 1, 0. I'm getting 0. Right? So what it means, x component is 0, y component is 0, z component is 0. So we have all three components 0. Why is it 0? Is it coincidence? The answer is no. Right? So this is one of the properties that you can see at the top part of your formula sheets. Right? In your formula sheets, look at the header. Right? You can see there are many formulas that we didn't use before because it's more like properties. Right? So let's observe this operation. What is gradient? Right? Gradient is all in terms of slope, which is represented. The line vectors are all in terms of straight lines. So how much is it changing in terms of x direction? Straight line. How much is it changing in terms of y direction? Straight line. How much is it changing in terms of z direction? Straight line. But we talked about this before. Cross product here. Alright, so technically this is curl. Curl is about rotational vector. If it is not rotational vector, the answer is 0. So what is the curl of a straight line? The answer is always 0. Right? So regardless of this expression. Because why? This is just an expression of scalar, but we are looking for gradient. So the moment it becomes a gradient, curl of gradient u must be equal to 0, regardless of what is u. Right? Because gradient itself becomes a straight line. So what is the curl of a straight line? Must be 0. Right? Because curl is looking for rotational vector. And straight line is not rotational vector. So what is the curl of a straight line? It must be 0. So this is like a property. You can find this property in your formula sheets. Look closely, alright, at the headers of the formula sheet, the first few entries, then you can locate this property. This is one of the properties. So next would be part C. I'm supposed to use the Laplacian formula. Del squared u. So let's use the Laplacian formula. Have to differentiate this first order. So when I differentiate this in terms of x, x becomes 1. So y, there is no x, this is 0. Then I have to differentiate in terms of y, first order, y becomes 1. This is 2y, z. Then differentiate this in terms of z. There is no z. This one z becomes 1. Right, so I'm not done yet. Remember, Laplacian means second order. So we have to differentiate one more time. Differentiate y in terms of x, 0. Differentiate x in terms of y, 0. Differentiate 2y, you get 2z because y becomes 1. And when you differentiate y in terms of z, is 0. So answer is 2z. Right? Part D. Remember, this answer is vector. you must put the brackets. This answer is supposed to be a vector, right? But we just write it as 0 because it is 0, right? 0 regards scalar vector is still 0, right? So it looks like as though it's scalar. This answer is scalar, so there is no brackets and so on, right? So next part, we are supposed to do this operation, divergence of del u. So divergence of del u. What is del u? This is my del u. So my del u is in terms of y, x plus 2yz y squared. 2yz x y. So I'm just substituting what is del u, right? I didn't want to write what is del u here, so I have substituted what is del u in terms of what we have expressed earlier. So I'm supposed to perform divergence now, right? Because we already find the gradient. This is already done. Del dot a vector, the answer is divergence, which is a scalar. And how do we perform divergence? X component, differentiate in terms of x, 0. Y component, differentiate this in terms of y, x becomes 0. 2yz becomes 2z because y becomes 1. And when you differentiate y squared in terms of z, answer is 0. So if you can't remember this, refer to the formula in your formulations. You're not expected to remember the formula, right? So, but when you try a few examples, you can recognize the pattern. So that's how the formula sticks in your mind without memorizing, except for curl, right? So curl is a bit tricky, but there is some pattern to it, right? If you notice, z and y, x and z, y and x. This is the x direction, therefore there is no x component. This is y direction, that is therefore there is no ay here. This is the z direction, therefore there is no az here. So we can use this way to recognize the formulas, right? So instead of just blindly memorizing them. So why is this answer same with this answer? Right? Because this is the definition of Laplacian. Right? So remember in the previous class we talked about Laplacian. Laplacian of a scalar is the divergence of gradient of the scalar. Divergence of gradient of the scalar, which is equal to Laplacian. So it should get the same answer. Right? So they use these two operations to derive the Laplacian formula actually. Right? The formula was derived through this divergence of gradient, right? So they took the gradient formula and they applied divergence formula to it, and then they got the simplified version, which is del d squared u over dx squared, and plus d squared u over dy squared and d squared u over dz squared. So the formula was derived from this divergence formula. So that is why we're getting the same answer. Alright, but we're not done yet. We're not looking for this, but we're supposed to evaluate this at point P. So what are they asking? They are asking you to do this at point P. So what is this? This is 2z. So at point P, this is the x coordinate, y coordinate, this is the z coordinate. Point P means it's a dot. So you're supposed to evaluate an expression at a particular dot. So you just take the parameters. But there is no x here, leave it. There is no y, leave it. There is z here. So 2 times 3 is positive 6. The fact that it is positive means it must be a source. Positive answer means source. Negative answer means sink. If it is 0 means not source, not sink. Refer to your notes with regards to the divergence. I have spoken about this before. Right, so even I have done some evaluation at a particular point to show you the 3 different conditions: source, sink, and not source, not sink. Right, so with that we are done with today's lecture. Right, I know it's a bit short, so which means we will compensate by giving you, you should have done more homework yesterday, so I think it should be just nice. So I'm done with this chapter. So moving on, next chapter is on electrostatic under free space. Right, don't miss the classes. Right, it's a bit continuous. Right, so we're going to talk about E, which is electric field strength. Then we're going to talk about F, which is electric force. Right, so the parameters are interrelated. So if you miss one of them, it will be hard for you to follow. Right, so we have E, we have F. Right, then we have D, electric flux density. Then we talk about psi, which is electric flux. Then we go into Gauss law. Right, so all these are interrelated. The formulas are linked to one to another, right? So it's better for you to follow the class as it is. So Thursday we will talk about Coulomb's law. Right? We are going to learn 2 things. What is the electric force formula and what is the electric field strength formula. right? So done for now. Okay, so do your homework as usual.